Alrighty, I'm going to throw some weird stuff at you. So I'm going to talk about reaction steps. And this is because most reactions do not occur in the same step. They have multiple steps to them. So if we have a first step, a second step, and a third step, here's some things to know about this step. The slowest one limits the reaction rate. So I know I'm going back to reaction rate stuff. But if we've calculated the reaction rate, and then we can calculate the reaction rate of each of the steps, the one with the matching one is going to be the one that limits that, because that becomes basically the bottleneck in the system for reaction steps. Now on an energy graph, so if I have time and energy, this could look like this. So I'm going to have my first hump, and I'm going to have a second hump, and then I'm going to have a third hill, and that's where I end up. Oh, I'm going to back that up. I'm going to go even lower here. So here would be my delta H. So this value went down from where I started. I know it's way over there, but it went down a little bit. So this would be an exothermic reaction. Now because I have 3 transition states, I know there's 3 steps in this reaction. The one with the highest amount of activation energy is going to be my slowest one, because it's going to take the most amount of time to collect enough particles with enough energy to push it through to the next step. So even though this one could have a higher hill, and from here it's the highest, so that would be, but because it's not, it's just here, this one would be. So it's the one from the total largest activation energy. And then I also, so that's reaction steps. Looking at them on an energy graph, the number of hills mark the number of reaction steps, and then each step can be endothermic and exothermic as well, and you can see that from the graph.